It's my pleasure to welcome Professor Scott Dodelson, who came all the way from Chicago University and the Fermi Lab, not only to give this public lecture, but to give our humanities 102 students on Monday morning a cosmological evolution lecture, and on Wednesday morning a biological evolution lecture. We are grateful. Professor Dodelson received his PhD in physics at Columbia University, did postdoctoral work at Harvard and then at Fermi Lab, where he was on the staff as scientist, and since has served as head of the theoretical astrophysics group and co-founder and interim director of the Fermi Center for Particle Astrophysics. He's the author of Modern Cosmology, which is a graduate textbook, and of 150 papers exploring the connection between particle physics, the very small, and cosmology, the very large. Dodelson is currently focusing on the dark energy survey going on in Chile and the South Pole telescope. I'm an English major, you understand how meaningful these are for me, okay? Which measures radiation left over from the earliest moments of time. Scott Dodelson is one of the first people that showed that the spatial geometry of the universe is flat. Thank you.
Thank you, and I just want to first thank my hosts, Professors Sevkin. They've really shown me a great time in Istanbul. It's a great opportunity to be in this amazing city and this really great university. So it's been a great week for me. I'd like to tell you a story today. And every story needs a picture on the cover, so you'll buy the book. And so this is the picture. We are made up of ordinary stuff, electrons and protons. All the chairs and tables and people in this room are made up of the same, let's call it normal matter. Part of the story is that in addition to that normal matter, actually most of the universe is made up of something completely different. There's about 5 times more dark matter than ordinary matter. So there's a mysterious substance called dark matter that pervades the universe and is much more abundant than the stuff that makes us up. In addition to that, a full 75%, 3/4 of the universe, is made up of an even more mysterious substance called dark energy. So I'd like to tell you the story of these substances and the role that they play in the formation of the universe. The story begins with 3 failures. So to understand these 3, let's walk through them one by one. The first failure we can understand if you look at the solar system. So remember, there are 8 or 9 planets in the solar system, and here they're ordered by how close they are to the sun. The closest planet is Mercury, then Venus, then us, then Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. So you see the ones that are closer are over here, the ones that are further away are over here. They're plotted, the height of them is how fast they're moving around the sun. And what you see is the ones that are closest to the sun are moving the fastest around, and the ones that are furthest away are moving much slower. And in fact, the pattern of these speeds, these rotation speeds around the center of the sun, can be predicted by our theories of gravity, Newton's theory of gravity, which was recently replaced by Einstein's theory of gravity. So we can actually predict the shape of this curve, and we get it exactly right. So that's a fact. We were emboldened by this success to move outwards. You know that our sun is only one of about 100 billion stars in our galaxy, the Milky Way. So we live right there. And so you might imagine then applying the same idea to the stars moving around the center of our galaxy. Just as the planets moving around the star should have this pattern of speeds, similarly, the stars moving around the center of our galaxy should have that pattern of speed. The ones that are further away should be moving around more slowly than the ones that are closer in, because most of the mass in the galaxy appears to be concentrated in the center, just like in the solar system. Most of the mass is concentrated in the sun. So we would expect then, when we measure the speeds of these stars, they would follow that typical pattern. About 40 years ago, Vera Rubin and collaborators started measuring the speeds of stars moving around the center, not only of our galaxy, but of other galaxies. And this is what they found. Here's a plot again of the distance from the center of the galaxy and how fast the stars are moving. There's about 4 or 5 different galaxies plotted here. In every single one, we do not see that characteristic pattern. Instead of the speeds falling off, we see just flat curves. So the stars, even very far away, are moving as fast as the ones that are close in. That's failure number 1. To understand the second failure of basic physics, to understand the world we live in, I'm going to introduce a metaphor. It's a parochial metaphor, so apologies. The metaphor is to look at a population map of the United States. And this is a map from about 220 years ago. So then there were only 13 states. And the colors show the number of people that lived in each area. So you can see traces of Boston and New York and Philadelphia. And what you see in those metropolitan areas, the population was pretty large. There were about 50 people per square mile in those urban centers. In the rural areas, there was almost no one per square mile. So in that early United States, that very early version of the United States, there was a big difference between the urban and the rural areas, but not that big a difference. In other words, the difference is there's 50 people per square mile versus 1 or 2. Kind of small inhomogeneities, if you like. Fast forward to today, it's a lot more states, people migrated out west. You still see traces of these primordial overdensities, but the most remarkable thing is in the numbers. It used to be in Manhattan there were 50 people. In New York, there were 50 people per square mile. Now there are 50,000 per square mile. So those inhomogeneities grew by a factor of 1,000 over the past 200 years. I find that fascinating, and I would argue that if there are among you excellent sociologists or economists, you would be able to predict and understand that evolution. You'd be able to take a look at the forces, the economic forces that force people to move into the cities, the racial forces that force people to move from south to north, the sociological forces that clumped people together. You would have a theory that would explain how we got from here to here. That would be the hallmark of a successful sociologist. So we'd like to do the same thing in a less parochial way for the universe at large. And we actually can do that because we use a trick. We can actually see the universe as it existed in the past and make maps just like the ones that I showed you about the United States. And the trick is as follows. It takes light a finite time to reach us, to travel from any object. So when we look at the sun outside, we're looking at the sun as it was 8 minutes ago. That means for all we know, the sun right now isn't there anymore. It's disappeared. We only know what the sun was like 8 minutes ago. More dramatically, when we look at the nearest star, it's 4 light years away, we're looking at that star as it was 4 years in the past, right around the time of the beginning of the Great Recession in the world. When we look, it's interesting. When we look at the center of our galaxy, we're looking at it as it was 25,000 years ago. And we can go further and further and further away. When we look at the most distant galaxies, we're seeing them as they were billions of years ago. So with this trick, when we look at things that are further away, we can make maps of the universe at different times. And when we can try that same game that I urged you to try with the United States, make map of the universe at an early time, at a late time, apply our basic law, our understanding of the laws, in this case it's just the basic laws of physics, and see if we can understand how the universe evolved from one state to another state. So that's the game. This is what the universe looks like today. This is a map made by the Sloan Digital Sky Survey, which has been in operation for about 20 years. We're sitting in the middle, and each one of these little dots here, and there are about 100 million of them, are themselves galaxies. So the Sloan Digital Sky Survey has mapped out galaxies out to about 1 billion light years away. This is what the universe looks like today. We can also make maps using the same trick of what the universe looked like much, much earlier on. This is a map made by the Planck satellite, the European-based Planck satellite, of what the universe looked like when it was only 400,000 years old. It's very, very different than it was today. Today, the number of molecules in this room is trillions of times larger than an average place in the universe. The universe today is very, very clumpy. There's spots like this that are very highly populated, and there are very, very underdense regions. There are the New York Cities of the universe, and there are the Wyomings of the universe that have nothing in them. Back then, when the universe was only 400,000 years old, there was no New York City, and there was no Wyoming, and there was no Istanbul. The universe was very uniform. Almost every place in the universe had the same amount of stuff in it. We can go a little bit further. This is a kind of a gross view of it. We can subtract off the average in this map, and we do see small deviations. So if you look at this map, same map, just we've subtracted off the average, and you see there are small deviations. So there were slightly more stuff here by about 1 part in 10,000 than there was over here. Again, very, very different than the universe today. Today it's very, very clumpy. Back then, the universe was very, very smooth. So now let me pose the question that I posed to the sociologists. Let me pose that to the physicists. How did the universe evolve from being very smooth to being very clumpy? That's a simple question, right? So one answer is that is gravity. A basic law of physics is gravity, that every mass attracts every other mass. So there are more people at this part of the room than in the back. So over the course of 13 billion years, all the matter would be attracted onto this part of the room. Let me show you a brief simulation of that. So this is a simulation starting with very smooth initial conditions and gradually evolving so that the slightly overdense regions attract more and more stuff until eventually we end up with this panoply of a cosmic web, filaments connected by filaments that are connecting clusters of galaxies, and we live in one of those galaxies in the center of one of those knots. So that's the qualitative idea that you start from something smooth and gravity acts to form very inhomogeneous, a very clumpy universe. The question is, does it work? So we're physicists, that's just an idea. We have to implement it by putting in numbers. So we can do that. We've measured the level of how inhomogeneous this map is. We know how inhomogeneous this map is. We just take our theory of gravity, we run those simulations, and we ask the question, could we have gotten from here, from this map at 400,000 years, to here, today? And the answer is no. If all that was going on was gravity, then we would not be here today. There would be just as, the contrast would no longer be 1 part in 10,000, it would be more like 1 part in 10. But basically, there would be the same amount of stuff here as there was in New York or Wyoming. So there would be no way to form the galaxies or the planets or the people or the stars that we see today. That's failure number 2. The third failure also emanates from Einstein's theory of gravity, which predicts that the universe should be expanding. The distances between objects should be getting larger as time evolves. That's a prediction of Einstein's theory of gravity. We can actually measure how fast the universe is expanding by using the following ramification of expansion. Imagine this room was getting larger in size. Everybody in the seats here would be moving further away from me. And if you think about it, in say the room doubled in size over an hour, the people in the front would be moving away at a speed of, say, 3 meters per hour, whereas the people in the back would be moving away, if it doubled, by 50 feet or 30 feet an hour. So that everyone would be moving away from me and from everyone else, and the people in the front, the closer people, would be moving away slower than the further people. This is exactly what was found by a Chicago astronomer, Edwin Hubble, in 1929. He plotted the distance of things, of galaxies, and the speed with which they are moving away from us. And he found this trend. Most of them are moving away, and the ones that are further away are moving faster. So it's interesting to note that, first of all, this experiment has been replicated about 100 times, and everyone going further and further away, and everyone's found the same thing, so this is a fact. The universe is expanding. Those of you who, many of you are highly technical. Those of you who are not highly technical probably are technical enough to remember that the slope of a line is important. So the slope of this line tells us how rapidly the universe is expanding. If it was very steep, it would tell us that the universe was expanding very rapidly, and if it was very shallow, it would tell us the universe was not expanding very rapidly at all. So the slope of this line actually has a name. It's called the Hubble constant, and it quantifies how fast the universe is expanding today. That begs the third question. We failed twice. This is the third question. Is the rate of expansion, which is quantified by that slope, is it speeding up or slowing down over time? So we can actually answer that question with the help of something that Shevza said in her introduction. The universe appears to be flat, and if we take that one fact that's observed to be true, and we stick that into Einstein's theory of general relativity, then we get the following equation. You might remember that Einstein's theory of general relativity equates the geometry of something with the energy of something. In the case of the universe at large, the geometry is quantified by how fast the universe is expanding, by this Hubble constant. The energy is the gravitational energy, the attraction of all of us and all other matter in the room. So what you see, imagine this room is expanding and the number of people in it remaining constant, the number of particles or the energy is remaining the same, but the volume's getting bigger, so the density is going to be going down. So in an expanding universe, this energy is going to be going down, and what that means is the geometry should be, the expansion rate should be going down as well. It's a very simple ramification of Einstein's theory of general relativity. You predict the universe should be expanding, but because of this equality, since the universe is getting more dilute, and there is this equality, you expect the expansion rate to be slowing down. So that's the third prediction. That prediction is wrong. Here's a plot of what the expansion rate should be doing, and this is a plot, an early plot of what the expansion rate is doing. This plot was, or some version of it was awarded Science Story of the Year about 15 years ago, and since has been verified by dozens of experiments. It comes from observations of distant supernova and also from these same early maps. They all agree that we're wrong. So that's the third failure. So we've begun this story of the universe with 3 failures. It's got to get better, right? So the second chapter is to introduce 2 new ideas to address these failures and the questions that they open up. The first 2 failures can be solved by positing the existence of something new called dark matter. And the way that would work is, think back to that primordial map of the United States. I wrote the population in New York is 45 per square mile. What if there were a hidden species in there that the census did not count? So that's essentially the solution here. There's dark matter lurking in this picture, but the picture doesn't capture the dark matter. It's like a shadow thing that's not picked up in the picture. And therefore, when we did our calculation of how clumpy the universe was back then, we were wrong. Really, there's something missing from the picture, and the dark matter is much clumpier than this stuff. So when we then run that movie forward, there actually is enough time to form the stars, planets, people, and galaxies that we see today. So dark matter solves this first problem. The idea is there's a hidden thing present in these early maps, and that's not captured by these early maps, and that enables structure to grow enough to form the stuff we see today. Dark matter also explains the problem with those stars far away not rotating too rapidly. The idea is here's the galaxy we see, but around that galaxy is a hidden sea of dark matter. So unlike the solar system, whose mass is concentrated in the central point, the mass in the galaxy is spread out all over the galaxy. So even the stars around here, they're moving around not just because of this stuff in the center, but because of all the stuff. So if you plug in that into your equations, you don't predict the fall off in velocity, you actually predict these flat rotation curves. So dark matter is a convenient way to solve both of those failures. It opens up a question, though: what is the dark matter? So we have a theory of all the particles in the universe that we're made up of. It's kind of the modern day periodic table. It says that all the elements are made up of fundamental quarks, electrons, neutrinos, just very simple building blocks of nature. About 12 different particles that make up, 16 different particles that make up everything. From these 16, you can make up everything. Dark matter is not on that table. So the question is, if dark matter really exists, what is it? And how does it talk to these normal things? How does it fit in? Does it signify some new, complete branch of physics that is yet to be discovered? So that's the first idea and question that it raises. The second idea is to solve the acceleration problem by introducing something called dark energy. So the idea is to keep Einstein's equation, keep this equality, just add another source of energy that exists in the universe. It's not you and me, it's something new. This new form of energy, in order to fit the data, has to have arisen only relatively recently, and that has led to the recent epoch where the expansion began to get faster. It's an innovative, provocative, wacky, make-it-up idea. What is it? What is the dark energy? So one thing we know is dark energy does not get diluted as the universe expands. If it did, then it would produce deceleration. So it's got to be something different than ordinary matter. It's got to be something different than dark matter, because dark matter too would get diluted. So it's something completely different. It might be energy just associated with empty space. So as space expands, maybe there's just energy, empty space itself has energy associated with it. It might be a signature that the universe has more than 3 dimensions. And some of those 4th or 5th or 6th dimensions are leaking in and causing the acceleration. Or make it up, because that's what physicists have been doing for the last 15 years. We have no idea what dark energy is. So these ideas and questions lead to plans. The first plan is to determine the identity of the dark matter. And we have a 3-pronged approach to do that. We can build big accelerators, such as the Large Hadron Collider in CERN, that can collide together particles like quarks and leptons that we can produce, and hope that those collisions will produce the dark matter. That's probe number 1. We can hope that these dark matter particles that exist everywhere in space will collide together and annihilate and produce junk that we see. We've put up satellites like the Fermi satellite to detect the debris that might emerge from the annihilation of 2 dark matter particles. And finally, we can build big underground labs and hope that a dark matter particle, which, remember, doesn't really interact very much with anything, will pass through the Earth and hit one of the nuclei in these ton-scale detectors, and we'll be able to detect the nucleus moving just a little bit. It's really an extraordinary series of experiments. There's about a dozen of these going on. So we have 3 ways of trying to find the dark matter and figure out what it is. For dark energy, as I said, we're pretty much clueless. So we've adopted the agnostic's point of view is we have to just measure what we can about it. And the way to do that is to go on making these maps of the past. So Shevza mentioned that I'm associated with this dark energy survey, which is one of the surveys which is built to do precisely this: measure the universe in the past, going back billions of years, to try to map out and see what the effects of dark energy try to figure out how dark energy affects those maps. So those are our probes. That's our idea for studying these mysterious substances, dark matter and dark energy. So in any other, most other scientists giving this talk would end here. And they'd have this beautiful summary saying we have this picture of the universe with these 96% of the universe is new stuff. The failures, these three different failures, can be explained by introducing this new stuff. We have a plan to find dark matter, and we have a plan to try to figure out, get some clues as to what dark energy is. Alpar mentioned to me, though, that I don't have to finish at 4 o'clock, so I have an additional 20 minutes, 25 minutes with you. So I'm not going to end the story here. I'm going to introduce a twist to the story and suggest that this story is part of a larger, older story. So let's go back about close to 200 years, and let me read you an excerpt from an undergraduate notebook from 1841. So this is a quote. "I formed a design in the beginning of this week." Are there any undergraduates here? Okay, the bar is high. Read this. "Formed a design in the beginning of this week of investigating as soon as possible after taking my degree the irregularities of the motion of Uranus." So this was the planet that was known, but its motion could not be explained by the force of gravity, which are yet unaccounted for, in order to find out whether they may be attributed to the action of an undiscovered planet beyond it. So this undergraduate proposed the existence of dark matter, an undiscovered planet, and if possible thence to determine the elements of its orbit which would lead to its discovery. So John Adams, 200 years ago, proposed the idea that there was this failure, the orbit of Uranus, and it could be explained by dark matter, a new planet. Not everybody believed that he was right, and unlike today, where I'm sure everyone listens to undergraduates, Adams informed his supervisor of his plans. He was in charge of the telescopes, but he didn't listen to him, so he didn't grant observing time in the telescope, because he believed the deviation was due to the fact that gravity was wrong, that Newton's theory of gravity was wrong. So right off the bat, you see this competition between two ideas. You're faced with a failure. Do you introduce something new, in this case a new planet, or do you change the laws? There's competition. A few years later, a French astronomer, Leverrier, and Adams had calculated the positions that this new planet might be in, and very quickly afterwards, the new planet of Neptune was discovered. So in this case, there was a failure, and there were two ideas. New stuff, change the laws, and the idea of new stuff won. There was another failure, the Mercury's orbit around the sun. People had measured that extremely precisely, and Newton's theory of gravity did not account for how Mercury precessed around the sun. The same Leverrier had this idea, must be something new, must be a new planet, right? In life, it seems to me, could be wrong, but it seems to me that when people hit on something that works for them, they just keep on doing it over and over again. This is what this guy Leverrier did. He proposed a new dark matter to explain this anomaly. He was very wrong. So in this case, it took Einstein to point out to us that this was not due to dark matter at all. This was due to a whole new way of thinking about space and time. And it was this observation that led Einstein to introduce his new theory of gravity, general relativity. So historically, we've been faced with these problems, these failures, and we've tried to attack it in one of two ways, either by introducing new things or by changing the laws. And it's gone different ways, different times. We have a similar dilemma today. We have the possibility that these failures can be explained with the dark sector, but increasingly, over the last 5 years or so, a number of us, we're still in the minority, but there's a number of us, are starting to think that maybe none of this exists. Maybe the thing we have to do is figure out a new way of thinking about space and time, of modifying gravity, going beyond Einstein's gravity. So that opens a new chapter in the book. Instead of talking about dark matter, figuring out where it fits into in the periodic table, and dark energy, trying to understand what crazy model people can come up with, we have a new plan or a new program in front of us, try to modify the theory of gravity to explain these failures. So that's exactly what we're trying to do. We're trying to come up with a new theory of space-time going beyond these new substances and going beyond Einstein. So I want to share with you our preliminary conclusions. It's been going on pretty intensely. It started slowly. Over the last 5 years, it's ramped up. I don't have an answer to tell you. The story's not finished yet. But we do have preliminary conclusions that I want to share with you. There's 3 conclusions I want to share with you. The first conclusion is Einstein, it turns out, was pretty smart. And coming up with a better theory of gravity is hard. So Einstein, he had this incredible intuition. He used things to develop his theory, like trains and clocks and elevators, to develop an intuition of the way the world works. He wasn't great at math. I mean, he was probably as good as you and me, but that wasn't his strong point. What he had was guiding principles guided on this physical intuition. We don't have that, right? Or at least none of us yet have displayed that skill. We are pretty good at math. We can write down complicated equations that most of you don't understand, but it turns out it doesn't really help us very much. Writing down complicated equations doesn't get you very far in life, it turns out. However, there have been hundreds, if not thousands, of papers with complicated equations for modifying gravity, but none of them have convinced anyone except the people who wrote the papers, because they're simply not compelling yet. So the first conclusion we have is Einstein is smart, and getting further than him is going to be hard. Here's the most technical plot in this talk. Our second conclusion. Remember, there were two sets of problems, one solved by dark matter, the other solved by what we call dark energy. You can modify gravity in different ways to solve those problems differently. The program to modify gravity to do away with dark matter, I think, is doomed for failure. And let me try to explain why. The theories of gravity that do away with dark matter don't seem to work. And they don't work because of this plot, which, as I say, is a little bit technical, but it's worth walking through. So on the x-axis here are the length scales. These are very large scales. These are very small scales. And this is a quantitative measure of how clumpy the universe is. The red points are the data. And the black points are models that have dark matter in them. They fit the data beautifully. The blue curves, the dashed and the dark blue, are 2 modified gravity models that do away with dark matter. So this is an early version, and you see this version fails miserably. It fails for 2 reasons. The grossest reason it fails is because the level of clumpiness is too low. One here signifies nonlinearity such that we would be able to exist. This early model doesn't even allow us to exist. This is a slightly more advanced version of this modified gravity model. We get to exist, so that's good. That's an important hurdle to be able to pass if you want to be credible. But you see that the prediction of this model for the clumpiness, for the pattern of clumpiness on length scales, it is completely different than the data. So technically, let me just say that these features are called baryon acoustic oscillations. Because there are no dark matter, these are, instead of becoming percent level things that you can kind of see hints of here, are 100% level things in models with no dark matter. So my feeling is that, although not everyone agrees with me, that modified theories of gravity that do away with dark matter are not going to work. That's preliminary conclusion number 2. Preliminary conclusion number 3 is that modifying gravity to do away with dark energy might work. There's a bunch of theories going on, and one thing that we have found, we're not quite as stupid as I made us seem, is that these new theories robustly predict that the pattern of structure in the universe, if you like, think back to the United States, the maps, the census maps of the United States across time, across those 220 years, would differ in a modified gravity model than they would in a model with dark energy. So we haven't yet, we have a couple of maps, that early one, that late one, but we don't yet have the fine resolution maps at many different times that enable us to test these modified gravity models. So we don't know. They could work, and I'm working really hard, and thousands of other people are as well, on these surveys like the Dark Energy Survey and the South Pole Telescope and a bunch of others, to try to test precisely this. Was Einstein right and there's dark energy, or do we need to go beyond Einstein? So that's our third preliminary conclusion. I want to close with the story with one final twist. It's a stunning twist. And first, let me just completely reorient us and about what we've been thinking. We started off with this picture of what's in the universe, and I argued there's new stuff, dark matter and dark energy in the universe. So we were talking about new stuff. There's another way to think about it, though, and that's in terms of how the universe evolved in time. So dark energy, this is a kind of a cartoon of what the universe looked like from the time it was very young, as captured in these early maps, to what it looks like today. And the outward going slopes of these lines indicate that the universe is accelerating today. So it's only in the past few billion years that the universe has started accelerating, and that means it's only in the past few billion years that dark energy has been important. On the other hand, to explain how structure grew from here to here, we had to introduce dark matter, and that had to operate over this whole period. So another way of thinking about dark matter and dark energy is they are our shorthand for understanding two different epochs in the universe. First, for when the universe is 400,000 years old till when it was a few billion years old, the epoch of structure formation. And second, the epoch today, when the universe is accelerating. So we have two mysteries that dominate these two epochs. And we don't know, is it dark matter, is it dark energy, or is it modified gravity? But think about it. We've talked this whole time about how things evolve, how the United States evolved from then till today, from how the universe evolved from this early map until today. You can think about it in terms of a person. How does a person evolve from a fetus to a grown-up? In the case of the person, it's obvious. The most interesting question, the most interesting thing is not how the person evolved from a fetus to an adult, but how the fetus got there in the first place, right? That's really pretty interesting. And similarly, in the case of the United States, how the United States got there, and in the universe also. A question that was asked in the humanities class by one of the students was, these are the seeds, these little inhomogeneities are the seeds out of which everything grew in terms of the stars, galaxies, planets, and people. But there's an earlier mystery, which is where did these seeds come from? So we started with two different substances that correspond, we now correspond to two epochs, but there's really a third mystery, which is where these came from. And in some ways, this is the biggest mystery of all, because this comes, where these came from, it corresponds to an epoch way before the ones that we've been talking about. So in some ways, it's true, it's a mystery, but we have little hope. We haven't solved these later mysteries, so we have little hope of solving this earlier one. We do, though, have an idea. And the idea it's an interesting idea. So let me show you a quick cartoon of that idea. The idea is that everywhere here in this room, there are little quantum mechanical fluctuations. That's what quantum mechanics does. It allows energy to be not conserved for a brief amount of time. So it's not surprising that in the very early universe, in the first fraction of a second, there were these quantum mechanical fluctuations in the density. The idea is inflation. That there was a brief epoch in the first fraction of a second during which those quantum mechanical fluctuations expanded exponentially rapidly. The universe accelerated for a first time. The current acceleration would be the second. And it whisked those perturbations, those microscopic perturbations, from the very, very small, quantum mechanics operates on the very, very small. The idea is that in the first fraction of a second, this epoch of inflation stretched those out so that they're huge, so that they, in fact, form the seeds of structure today. And there's even a way to test this idea. So the idea is that quantum mechanics produce these things, if that idea is correct, right? These things, they're really big. I mean, each one of these little things here is about 500 light years across, so they're huge. But the idea is they started off as microscopic, smaller than your fingernail fluctuations that were whisked to be huge lengths by inflation. There's a way to test that idea, and the way is as follows. During inflation, in addition to the fluctuations in the density, there were also fluctuations in space and time. Those are called gravitational waves. And just like inflation whisked the density perturbations to be very big, it also should have made the gravitational waves to be very big. So we should be able to see those stretched gravitational waves that were produced during inflation. But we've seen so far only these density perturbations, and it doesn't really, you could be an optimist, you undergraduates, you're young, but those of us who are a little older, we're kind of cynical, and we just don't think that things like this change overnight. We haven't solved those later mysteries, dark matter and dark energy. We have little hope that we'll be able to detect these primordial gravitational waves that were produced when the universe was only 10 to the minus 35 seconds old. That's the way we all felt until 7 weeks ago. 7 weeks ago, this changed. The time when lots of things were happening that everyone will eventually forget. This was also happening that no one will ever forget, and that is that there were space ripples seen as a smoking gun of the Big Bang. This is the most reputable paper in the United States, and the keynote of an important story is it's above the fold. So this is an above the fold story, one of the few science stories ever above the fold in the New York Times. Of course, you realized it here, you tweeted about it, and so everyone across the world was recognizing the importance of this story. So we actually have apparently detected these primordial gravitational waves. So the story that we started out with about dark matter and dark energy really transforms into, is it modified gravity? And it goes further and transforms into the question of what powered these two, and now three epochs, inflation, structure formation, and the later time of acceleration. The story then has a happy ending, so I want to conclude the story with this brief video showing the response of somebody who first proposed the idea of inflation.
Today I'm going to deliver a news to Professor Andre Linde, who is the founding father of inflation. So inflation is the theory about the bang of Big Bang. It explains why we have all this stuff in the universe. So today I'm going to tell him our experiment, BICEP 2, based at South Pole, has found the smoking gun evidence of inflation. He has no idea that I'm coming.
Oh, wow.
So I have a surprise for you.
Wow.
It's 5 sigma at 0.2.
Discovery.
Yes.
What? Just a second. Can you repeat it?
5 sigma, as clear as day, R of 0.2.
Can you repeat it again?
R 0.2 plus minus
0.2.
If we stop there. We don't expect anybody. Renata tells it's probably some kind of delivery. Did you order anything? Yeah, I ordered it 30 years ago. Finally, it arrived.
Cheers, cheers.
Congratulations. Oh my God, I'm going to break something. We are talking right now about billions of billions of billions of millions of seconds after the Big Bang. So we see the face of the Big Bang. It is an image of these gravitational waves, which are purely quantum gravity feature of what was produced in the Big Bang. So this is a remaining part of the story.
It's really hard.
They all there. They all three
there.
different experiments.
Yes.
If this is true, this is a moment of understanding of nature of such a magnitude that it just overwhelms. And let's see, let's just hope that it's not a trick. I always live with this feeling, what if I'm tricked? What if I believe into this just because it is beautiful? What if, yes. So this is really helpful to have events like that. It's really, really helpful. Thank you so much for doing it for us.
So in the United States, we know we have to end all stories with happy endings. So my conclusions are that there are 3 strange epochs in the history of the universe. Amazingly, we apparently understand the earliest of them all, inflation, driven by physics at unimaginably high energy and early times. The last 2 epochs, structure formation and acceleration, we do not understand. So there are undergraduates in the room, get to work. To do so, you're going to have to resolve an age-old debate when you're faced with failure. Do you introduce new things, or do you change the laws? Thank you. want the microphone? I don't know.
Discovered quantum gravity.
No sound.
If we discover quantum gravity, will these results change dramatically, or we don't have right now quantum theory of gravity? We are using these classical concepts.
Right, so the detection 7 weeks ago, if it's confirmed, if it's not tricking us, is of a quantum mechanical effect. And it happened when the universe was very, very young and the energies were very, very high. So in physics, there's a scale, a mass scale that corresponds to gravity. It's called the Planck scale. The physics that drove inflation is close to the Planck scale. In fact, the field that drove inflation had to change by an amount greater than the Planck scale to account for the observation. So this is the beginning. As we make further observations over the next decade of these primordial gravitational waves, I believe we will get a handle on a question that has plagued physicists for 100 years. How do we reconcile these two theories of quantum mechanics and gravity? This is, I think, the only way that we see right now to do that. Does that address your question?
Partially, I mean, all this dark energy issue, dark matter issue, will they change if we have quantum gravity theory? Gravity theory also will change dramatically. Now we are playing around the Einstein theory of gravity.
So it's possible, again, I'm older and cynical. I don't think we're going to understand quantum gravity very quickly, but let's say we did. And that doesn't guarantee that we'll understand dark energy and dark matter for an important reason. Quantum gravity is a description of how gravity works at very high energies when gravity is strong. Dark matter, and especially dark energy, are in the opposite regime. They're in the regime where gravity is weak. So there's no good reasons to think if we understand gravity in what's called the ultraviolet end, and when it's strong, that will suddenly, a light bulb will go on and we'll know what's going on when the gravity is weak. The one exception to that criticism is there's an idea called holography that might enable us to connect the very strong scales of gravity with the very weak scales. So far, however, that idea has not worked to explain the acceleration.
Can you give some information about this dark energy survey? Are you going to look at supernovas?
Right. So the dark energy survey will use 4 different techniques of getting at dark energy or modified gravity. The first is looking at distant supernova. The second is looking at this feature, this baryon acoustic oscillation feature that we looked at a little bit. The third is to measure the abundance of very big things, galaxy clusters. That abundance is a sensitive probe of these theories. And the final thing is to look at gravitational lensing, how light gets distorted as it traverses the universe. So those 4 probes that will culminate after 5 years of the survey will give us greater understanding about the dark energy. So that's it, those 4 probes. And that's the cartoon summary of the dark energy survey. What I'm actually working on is I'm head of a working group in the survey that breaks that down, that says that all these probes are combined. So when you combine those probes, you actually can get more information. So it's kind of fun. It's actually a very exciting time trying to figure out the best ways to attack these questions.
Can you pass that to the third row? There's a question.
I wanted to ask, I mean, in the couple of last years, there has been some great breakthroughs through certain discoveries. I mean, recently the gravitational waves. such a discovery. Do you think that we are waiting for any such discoveries?
I'm sorry, I missed the question. Do we think? Do you think there will be more discoveries?
Yes, I mean, in your opinion, are there any big discoveries to be made in the upcoming years?
So, you're asking me at the wrong time. Because 7 weeks ago, I would have said, you know, things haven't really changed much in a long time, so I'm a little cynical. Really, this has been, for me, the biggest discovery. I didn't make it, but the biggest discovery ever in my career. Watching that, it's been amazing. It sounds like some of you, many of you knew of this and were excited about it as well. Just to give you a sense of how exciting it was, there was a press conference on Monday, March 18th, I think. They announced it in advance, and I thought, how is the world going to come together and talk about this result? So I'm a little bit older than most of you, so I can't use Twitter or anything, so I started a Facebook group. Within about an hour, we had 300 people, the leaders in the field, and this group now has about 1,100 people in it. And during the press conference, they released the papers, everyone was typing and look at figure 4, look at figure 3, look at this, look at that. There was just so much excitement around the world. Andre Linde captured it a little bit, but all of us felt the same way, I think. It was really amazing. So you ask me, is there going to be another discovery like that in a year? I think you're being a little impatient, but I'm optimistic that people like you will show us new ways of thinking about things, and that science will move forward, and there will be great discoveries in the future. Yeah.
Other questions? Can you pass it front?
There are also several theories alternative to Big Bang theory. Is the discovery of gravitational waves a sign in the direction of Big Bang, or can it be linked to other alternatives? Right.
So let's put aside the question of the Big Bang theory, because I don't like that word, but the notion that the universe is expanding is a fact. There's just, I don't think there's any reputable scientists who disagree with that. So any way of understanding the universe has to have that as the centerpiece. Similarly, that map, when the universe is 400,000 years old, has been analyzed and analyzed and analyzed, and it agrees beautifully with our basic picture of how structure formed in the early universe. So the number of alternatives are dwindling rapidly. The reason why I don't like the word Big Bang, because it implies that there was an explosion from a point. In fact, that's not true. Everywhere the universe was the same. There is no one point. There's no center of the universe. The Big Bang, I think, is not a very good descriptive way to describe it. But the one case where there were two competing alternatives was in the question of where these primordial seeds came from. And there was an idea about inflation, and there was another idea that called the ekpyrotic universe, that the universe underwent collapses and expansions, collapses and expansions. That second idea, I think, even the people who put it forward, who are scientists of great renown, who I respect very much, now agree is ruled out. So the theory of inflation is standing. It's actually the simplest idea to explain that, and that alternative at least has been ruled out. Who knows? There's young people here, they'll come up with new ideas. But for now, that theory does seem to be the right way to think about the early universe.
Any other questions? Okay, one more, and then we end.
One reason why this cosmological constant problem is such a big problem is because if you write it as an energy density, it's an incredibly small energy density. So if you think about this problem in terms of modifying gravity, is there some natural reason why you might expect to come up with such a small number?
Right, so then you're absolutely right that modified gravity models sidestep the question of why the cosmological constant is small. All they do is they implicitly assume that it's zero. So, and in fact, some modified gravity theories are worse. They actually put it in without telling you. But you're absolutely right. They don't solve it. So no one has yet, and I should have said that, so the cosmological constant problem is the following. The energy associated with empty space is actually a good candidate for driving the acceleration, because we know that there are these quantum mechanical fluctuations that should provide energy. It's just that when we come to calculate it, we're off, but we're way off. It's way too big. So that's the cosmological constant problem, why that energy is so big. No one has a good answer to that, but many of us feel that if we can't solve it, it would be much easier to accommodate if it was truly zero. Because then maybe there's some symmetry principle that makes it zero, and then the acceleration will be driven by something else. The notion that it's very, very small and just happens to be coming into play now seems kind of crazy to me. So in that sense, the modified gravity thing is in my mind, a little bit of an advantage, but you're right, it does not solve the cosmological constant problem. Yeah.
Okay, thank you.
Good.